All right, so let's get going. Good morning, everyone. Welcome to another edition of the Finite Element Seminar at Livermore. This is, believe it or not, the 50th talk in this seminar series. And I don't know when that happened. It's been a lot of fun. It's my pleasure today to introduce Dave and Edward from King's College in London, and they're going to tell us about some really interesting work in Nektar++ on MLIR. I know there's a lot of interest in this area, and we really appreciate you guys coming and sharing your experience. Dave, the floor is yours.
Well, thanks very much, Daniel, for both the very nice introduction and the invitation to speak. I didn't realize it'd be the 50th speaker, so that's a unique privilege, but I'm very happy to be here. So we're going to give that kind of talk in two halves a little bit. I will kind of set the scene for perhaps those of you that don't know us or what we do, and our code Nektar++. And then I'll hand over to Edward for the actually kind of more interesting part of the talk, which, as Daniel says, will focus on MLIR and the kind of intermediate representation, which we're calling NektarIR, that we're writing. So from the title, you can see we're kind of trying to target a compiler specifically for high-order finite element operations on heterogeneous hardware. So I'll kind of set a little bit of motivation out what we do in my group and the kind of problems we're interested in solving, and I'll talk a little bit about our code Nektar++ and where we are in the kind of current hardware landscape with that code. I'll then talk about a topic that I've been kind of interested in for a number of years now, and with others in our group, and Mike Kirby, for example, on the call here, we did some of the first work on this, looking at efficient high-order finite element operations, but specifically on elements that are not hexahedra and quadrilaterals. So we're really interested in elements that like tetrahedra, prismatic elements, and so on, and how we can evaluate operations there efficiently. And then I'll hand over to Edward for the second half of the talk and a quick summary at the end. So what are we actually interested in our group? One of the big interests is essentially problems that kind of look like this. So if you're a fan of Formula One or motorsport, you might recognize this kind of geometry. This is a simplified geometry we call the imperial front wing. It's a kind of prototype F1 geometry, and it has quite a lot of kind of interesting geometry that really companies like this is originally from a McLaren car, and they are very interested in high fidelity simulation and looking at what happens with a great deal of accuracy to the kind of vortices and fluid dynamic structures that are generated by some of the kind of, you can see sharp corners that are deliberately introduced into the design here to promote separation in particular areas, and then see how that impacts performance downstream of the car. And really, it's kind of a prototypical example of the kind of thing that we're interested in. We're really interested in scale resolving simulations, but specifically for kind of highly complicated geometries. And those kind of geometries will be interest to industry, either in the fluid dynamics world or in other areas like particularly I'm working closely with the UK Atomic Energy Authority at the moment on fusion as well. So we have a range of interests, but they really focus around this complicated geometry aspect. So to give you an idea of some of the things that we kind of do at the moment with the code, this is some recent work from a former PhD student, James Slaughter at Imperial, who we were looking at kind of taking essentially a slice through this front wing section, so you can see the free element and the multi-element downfall, and then looking very closely with a rolling road about what happens to the ground effect, particularly with this kind of configuration, and in very fine detail, looking at separation, looking at the kind of flow structures that are generated, what happens in the wake, and so forth. And then scaling that up more recently, we've been interested in these kind of more full 3D simulations where we introduce as well a rotating wheel, as it would be on a real car behind this F1 wing, and then seeing what the result is on the kind of downstream vortices. And these are kind of interesting problems from the perspective of industry, because the kind of classical tools they used to don't give this kind of insight, and there's often a lot of kind of internal kind of correction for results from things like RANs, from things like LES, kind of low order LES or kind of DES type simulations, where they're interested in what happens to a higher and greater extent of accuracy with a simulation. And so we've built this kind of suite of tools specifically around these kind of problems in this code that we call Nektar++, which is kind of similar to FEM and its kind of aims and ambitions and other frameworks as well, like DL2, where we're really interested in trying to apply these kind of methods to a range of problems. So I didn't know exactly who would be in the audience, and I suspect I'm preaching to the choir a little bit. But for those that don't know much about kind of high order methods, and particularly Nektar++ being a high order spectral element code, for these kind of problems, this kind of numerical solution is very is a really ideal fit. From the kind of mathematical perspective, obviously we have this kind of exponential decay where, you know, just refinement in terms of element size h is it's okay, but actually increasing in terms of p and enriching the polynomial space gives you a much better appreciation of accuracy. Increasing p also leads to a lot of favorable diffusion and dispersion characteristics for these kinds of problems where you're interested in tracking spatial structures, large spatial structures like vortices across a long length scale, potentially the whole length of Formula One car. You want to introduce as minimal kind of diffusion as you possibly can. And so this video here is just kind of an illustrative example of that, where you kind of have this rotating Gaussian that is at the same number of degrees of freedom approximately, but at increasingly higher polynomial order, and you see their ability to kind of resolve that Gaussian a lot more accurately as you increase p. For us particularly as well, it's this kind of classical combination of you know, the higher accuracies of a traditional spectral code, but then kind of held inside these local elements where we're able to capture the kind of complicated domains and break this up into some kind of mesh of triangles, quadrilaterals in 2D or tetrahedra, etc. in 3D. And that gives us the ability to model some of the, this is an example of just a DLRF1 engine to cell here. And for the purposes of this talk, probably the most important thing is the kind of computational advantage. So this doesn't come for free. None of these things are free. We have to pay for them, and we pay for them with flops. But actually, it turns out that's beneficial in our current hardware landscape in terms of the memory bandwidth being the real bottleneck in terms of being able to use hardware efficiently, either GPU or CPU. So the fact that we have to do more flops gives us some of these benefits for little additional cost compared to if you were at lower polynomial order. So that's going to be the focus today, and really the challenge for us is kind of motivating why we're interested in these kind of non-tensorial elements. So I think it's pretty widely appreciated that the most efficient elements at high order are hexahedra, or in 3D, or quadrilaterals in 2D. We have the ability there to kind of, you have the most structure, you have an easy tensor product to higher dimensions of one-dimensional basis functions that you can use techniques like subfactorization to speed up and so forth. So it's been shown repeatedly that these are the most efficient elements to use. The problem is that if one is interested in these kind of more complicated geometries, unstructured hex only, or dare I say even kind of hex dominant meshing is really still quite an open problem. There are certainly, you know, it's not to say it's impossible, but it takes a lot of time and effort to create one of these kind of hex only or hex dominant meshes. So for example, if you look at the Imperial front wing, the kind of mesh that we were running that kind of simulation on I showed you before, this is a kind of prototypical example of the meshes we run, you know, very frequently, where we construct meshes from prisms in boundary layer areas, and then we use tetrahedra to fill out the rest of the space, and that allows us to deal with capturing the kind of geometric fidelity we need for actually kind of bending these elements to fit the CAD geometry underneath it. And as well, dealing with some of these really irritating areas like the slot gaps between the kind of different the three different aerofoil sections and so on. So without these kind of elements, we wouldn't be able to run these kind of simulations at high order for this kind of configuration. So really, the question for me has been how we can try to make those operations on those elements. Certainly, we're not going to be able to make them as efficient as hexahedra, but can we maximize the efficiency as best we can? So we do this in this code Nektar++, and it's an open source framework for what we call the spectral HP element method, which I'll discuss a little bit more specifically what I mean by that in a couple of slides. And really, it was motivated from a kind of precursor code called Nektar, which focused exclusively on fluids. where we wanted to kind of expand these methods to many areas, not just fluids. So we designed this really with complicated geometries in mind, rather than kind of just structured grids and so forth. And really the kind of reason for that is to have the hybrid meshes of multiple element types in either 2 or 3 dimensions. We designed it to try to support a range of different discretizations. So we have our kind of classical continuous Galerkin formulation, C0 formulation that, is the classical finite element type method, as well as the more kind of modern stuff like discontinuous Galerkin. At scales, ideally from kind of desktop all the way through to the biggest HPC system. So being able to use a sort of range of scales is really important, because what we found generally is people have a lot of different use cases, and it's not always necessary that we want to run on a massive great big HPC, but we still want to kind of support the best performance we can on people's laptops and kind of local workstations and such. We have a range of solvers. I'm going to talk mostly about just the incompressible Navier-Stokes solver, just to give you a flavor of one of them, but we have a range of different solvers, including compressible Navier-Stokes, and it does have a fairly kind of feature-rich environment at this point, because they've been, we've benefited from a significant amount of development. This has started in 2004, so or thereabouts, by Mike and Spencer Sherwin at Imperial. And we've really built a lot of architecture on top of that initial foundation. So, for example, our compressible Navier-Stokes has a variety of features, including variable polynomial order, these non-conformal meshes, different equations of state for different gas models and such. So we've spent quite a lot of time developing this. But the problem, I suppose, is that underneath that development, the hardware has continued to evolve. And we started out really as a CPU-only code. So now, I guess for the rest of my kind of half of the talk, I'll talk really about a significant redevelopment effort that we've been putting in over the last couple of years. And that is really to get all of this stuff working and being efficient, not only on the CPU, but on the GPU. So I'm going to talk a little bit about the strategies that we're employing for that, the kind of implementation choices we're making, and so on. Just to highlight, this is not like just, a one-person effort. There's a whole range of researchers. So these are just the kind of people involved from 4 different kind of institutions. So Imperial, King's, University of Utah, and most in there as well at Newcastle University in the UK. So we have a whole range of inputs from a massive range of people. So this is certainly a big team effort to get this thing working, and we're very grateful to everyone for their contributions. Just to set the scene a little bit, I don't really have a lot of time to talk about the entire kind of numerical discretization, but I'll focus on the incompressible solver and just break it down into what that looks like. Of course, we start with Navier-Stokes, and we're applying this kind of stiffly stable velocity correction scheme. So this is for anybody who's worked in this area before, this is a very standard kind of technique at this point. It's implemented in a wide range of solvers, for example, NEC 5000, NektarIR, NECO, and so forth. And it's kind of an implicit-explicit scheme where we have an explicit affection step, so a kind of multi-stage affection step, followed by 4 scalar solves. One, firstly, for a pressure Poisson correction, one for a pressure Poisson equation, and then 3 scalar Helmholtz solves for the velocity correction stage. So in terms of kind of a flowchart, you kind of do the advection followed by this kind of these 4 scalar equations, and then you time march from there. And this is shown with the appropriate pressure boundary condition to give you kind of high order time accuracy, typically delta t to the 2 or 3. So the vast majority of the time, if you're interested in making this fast, the advection is kind of a trivially parallelizable thing, kind of works essentially on just local elements one at a time. But the vast majority of the runtime for a solver like this is spent in the linear solves. So solving these equations for the Poisson equation and the Helmholtz. And there are really 2 constituent parts to that. We use, obviously, as symmetric systems, we just use a conjugate gradient method. And so we need fast matrix vector operators, and we need good preconditions. I'm only going to talk about the matrix vector operators today, and that's the thing we're really focused on for the purposes of this talk. So just to give you one final example of this thing actually being used in action, this is a kind of track car. So if you've got a bunch of money burning a hole in your pocket, you can probably buy one of these things. They're usually set up by small companies. And in this case, there's a specific company, Elemental, who put this car together. And because it costs a lot of money to put one of these on a wind tunnel, we were able to provide a kind of virtual wind tunnel for them, and went through a couple of kind of design iterations purely using Nektar and some other commercial tools and CFD only to really get a clear picture of where downforce has been generated on this. And so if you're interested in this, there's a kind of a review paper and that you can have a look at, which is listed down below. So let me kind of talk about these kernels for high-order FEM. So the scene, for those that I guess are not aware, is that on modern hardware, i.e. Modern GPUs, modern CPUs, you have an awful lot of flops, usually because you have an awful lot of compute cores on each, either in the case of a CPU, you have many sockets, or if you're on GPU, you'll have a stream multiprocessor, and lots of them. There's a CUDA cores to back those up, for example, on NVIDIA hardware. So we have a lot of flops. But the challenge is really getting the data onto and off of the compute efficiently. So we really need to do as many operations as we can with data that's being transferred in order for us to actually be able to use the hardware effectively. And that's a concept of arithmetic intensity, that we need these codes and algorithms, such as for these kind of higher order methods. As you increase P, you can kind of tune this arithmetic intensity to target the hardware that you're interested in. On the CPU particularly, you have to exploit as well SIMD parallelism quite clearly, and SIMT, I suppose, as well on GPUs. There's a similar kind of concept where we're explicitly using things like the AVX registers and thinking very carefully about how those are being utilized. Because if you're not making full use of AVX and FMA, you're leaving an awful lot of flops potentially on the table as well, that the CPUs really rely on to kind of hit those peak flop figures that are kind of published. And the way we do this is kind of fairly well established by codes like MFEM, DL2, as well as ourselves and others. And it really relies on this concept of matrix tree methods, where we're not actually forming a big global system for these matrices we're solving. We're just evaluating that action on an element by element basis. And we're using some factorization and tensor contraction or tensor contractions, depending on how you want to call this, in order to take the very large amount of flops that you would do that you perform to do this, and just reduce that down to something that's more manageable and allows us to kind of sit in the kind of performance range on this hardware. So really, we've been examining whether this can be applied to more general element types, particularly some factorization, because this relies on this tensor product structure of a quad or a hex in order to work in the first place. So let me talk about the spectral HP element, what I mean by this. There are some kind of defining features, I would say, of the spectral HP method, rather than kind of the classical nodal-based Lagrange shape function spectral element method. And the first is that we have this kind of tensor product basis. In this case, it's the C0 basis you can see in books like Connie, Dawkins, and Sherwin, where we essentially augment the linear modes of the P1 formulation with these kind of higher order modes. And we do that in a way that preserves a tensor product basis. So we define this on what we call the collapse coordinates. So these are always hexahedra, and with these eta coordinates. And then those are mapped via a Duffy transformation onto a reference element. So in this case, a triangle. And so these shape functions live essentially on this collapse coordinate space, and they still have this tensor product structure, but they still span the appropriate polynomial space for the element you're interested in. And then we do the usual thing, which is that we have some kind of geometric fitting aspect where we map that reference elements of the world space. And you can see that in general, we're going to want to make the elements curvilinear so that they align to whatever geometry of interest that we have. And then from all of that, we do that element by element. And then the kind of naive way to kind of solve a problem, like the Helmholtz equation, would be to form the Laplacian, the mass matrix, and solve this system for our U hats. So in terms of, oops, I have to skip through this again because I pressed backwards by mistake. So in terms of the kind of mathematics of this, we obviously have our expansion in terms of a particular number of modes on each element, and then we split that up into our kind of two coordinate directions for P and Q here, where we have generally not got any collocation, i.e. we're not using kind of interpolants like Lagrange interpolants. We have a set of polynomial functions with weights U hat PQ, and then we have a set of quadrature points which we're interested in evaluating things in a kind of physical space, so things like derivatives and such. So this is generally not a collocated method in that sense. And indeed, as well, we typically will consider the case, at least in Nektar, where we allow P and Q, which are the directions, the polynomial, the order of the polynomial in each direction within the element. This order can vary as well. So P does not necessarily have to be equal to Q in this expression. This is essentially the top box here is a representation of something like a quadrilateral. For things like tetrahedra, we do the exact same thing, but now our kind of polynomial space is reduced to account for the fact that we're on a tetrahedron versus a hexahedron, for example. And so we have this kind of more complicated indexing, where we have basis functions now that differ in the different directions, and they're also kind of hierarchical. So you have a one-dimensional one, and then a PQ and a PQR as well. So it's this kind of principle applies, but you can see as well, these kind of inner loops of the summations become more complicated. They're not just simple Q, P equals 0 to P, Q equals 0 to Q. We have kind of this more complicated structure that we have to exploit. The other thing that we tend to do is that in using the Duffy transformation to collapse onto the reference element, this introduces a singularity where you've collapsed this. And that singularity is removable, and you can show it doesn't kind of affect your expansion order. But from an implementation perspective, it's a bit of a pain because it requires some kind of special treatment. So what we tend to do as well is to use a non-uniform quadrature. So for a triangle, for example, we might select a standard Gauss-Lobato quadrature for the direction that's not being collapsed. And then for the direction that is collapsed, we'd use something like a Gauss-Rodau quadrature where you're excluding the endpoint that happens to be corresponding to your singularity where you've collapsed the shape down. So I'll talk a little bit about kind of implementation choices. And as I said, kind of the naive way to do this is to form a global matrix, which is almost universally a terrible idea for higher order methods. Because you're not using any of the structure that you actually have within the elements. What we've done for a long time is to use kind of local evaluation. And this is what kind of Nektar was originally built on, which is to create an element that is local to each element. So we have these little dense matrices that are kind of compact. They have a nice structure. They can be evaluated quickly. And then we use an assembly to kind of bind those together, for example, for a C0 type operation. With a matrix-free method, we actually take each of those local matrices and we never construct it. We use instead, you can view it as a series of kind of smaller one-dimensional matrix multiplications to essentially evaluate the action of that matrix multiplication. So you still have the assembly between elements, but instead of generating a dense matrix, which would have a large memory cost, we use shape functions that live on the 1D reference element that can be used to evaluate the action. But that's more expensive to do. However, we have this trick called subfactorization that allows us to kind of get around this, which I have on the next slide. So kind of left to right here, you have this kind of hierarchy of increasing arithmetic intensity. So this performance at high P, we don't assemble the matrix, but we evaluate its action. And the trick is a fairly standard one. So in these expressions where from the previous slides, we essentially notice that all the terms in terms of Q can be evaluated and stored. So the bracketed terms here can be stored. And that allows us, storing these partial sums allows us to reduce the operator cost from P to the 2D down to P to the D plus 1, which is a significant saving and allows us to kind of reduce the flops to somewhere where it's more manageable on the spectrum of arithmetic intensity. And for triangles, tetrahedra, etc., with this kind of expansion in terms of the shape functions, with this phi p and phi pq and this last expression, you can do the exact same thing. It's just more complicated. One has to account for the indexing a little bit more, but it's still theoretically possible. So the question is it really worth doing? There's a third option as well, which I'll talk about because it's in some of our results slides in a minute, which is what we call the standard matrix approach. So this is an approach where you can compute an operator matrix on the standard element. So you kind of throw some factorization out the window and you say, right, I have a matrix that represents the backward transform or the inner product operator or whatever operator you're interested in on a particular standard element. And then you can apply a kind of large skinny matrix multiplication. So where the rank in one direction is just the number of degrees of freedom on an element, and then you have a very large right-hand side matrix, which has all the degrees of freedom as the number of columns. And that allows you to essentially cast the problem into a very big but skinny dgem or gem type operation. The only problem is that you have to kind of incorporate some appropriate metrics into that. So you have to, for example, account for Jacobians, derivative factors, and so forth. And it may be as well that you need to do multiple matrix operators depending on the complexity of your operation. So it disregards some factorization, but it does allow you the possibility to exploit kind of these more optimized small matrix implementations, such as libxsmm, which is this kind of very cool library for generating just-in-time compiled kernels for gem operations for very small matrices. And you can do a similar thing on GPU. You can just chunk this into small groups that are kind of appropriately parallelized over threads. So when we were going about the implementation or re-implementation of a lot of stuff, we've made some kind of key choices. The first is kind of an obvious one, which is take all the elements you have and then group them in as best you can. So particularly by the type of the element, polynomial order, what integration order you're interested in, and whether that element is what we call curved or regular, i.e. the Jacobian is constant in space or varies in space. And then in terms of operator efficiency, on the CPU particularly, we observed there's a kind of couple of ways that you could lay the data out. You can either choose to lay it out element by element, so all the data for element 1 followed by element 2 and so on. Or you can take a small group of 4 or 8 elements and you can interleave their data. So you store degree of freedom 1 for elements 1 through 4, followed by degree of freedom 2 for elements 1 by 4 and so on in this example. And the reason we do that is explicitly to exploit whatever vectorization might be possible on the hardware of choice. So if you can imagine taking all of your elements and grouping them into these chunks of 4 blocks, then you can do operations like these dot products of basis functions can be done over elements of size of the vector width. So for example, if you're in the CPU and you have a 256-bit AVX2 operation, you can leverage that SIMD by reordering your data such that you can hit it with these basis functions and get each one of these dot products in this case in a single cycle, or each element of the dot product in a single cycle. And you can also exploit your FMAs this way. The way we do that is to kind of heavily use a C++ data type that encodes operations, and we don't trust the compiler to auto-vectorize this, so we explicitly use compiler intrinsics to target the different AVX2, AVX512, and even like SE2, for example, on ARM type architectures as well. And then we use templating on quite a few parameters I'll talk about in a minute to allow compilers to do as much optimization as they can, either to unroll loops, either to do kernel fusion and aggressive kernel fusion at that, or register blocking and so on. So these are all very important aspects for performance that you potentially will neglect if you don't have them at compile time. In terms of the GPU, you have kind of a richer memory and execution hierarchy. So your you might have a 32 or 64 threads, 32 on NVIDIA, 64 on AMD, and they kind of live in the streaming multiprocessor. And you have, therefore, more cores, more parallelism, less memory per core, more cache pressures as well. And so you have to consider different memory storage options as well as the kind of parallelism you want to use. The one option is just to take, in this case, you're seeing, the 32 cores that would live in a warp, and the circles represent an element. So you say, okay, I'm going to give an element to each core, and each thread owns an entire element, and data then gets interleaved into a big 32 wide block, just as in the CPU implementation I just showed you. The other option is that you can note at higher polynomial orders, you have quite a lot of work to do for each thread in the top case. So you say, okay, instead I'm going to try and parallelize over the elements themselves. So an element gets assigned to an entire block of threads, and each thread is given a quadrature point or a mode to process depending on the operator you're interested in. So then you can start to look at what happens for different element types and what happens for different implementation strategies. So this is for the GPU, and there's kind of 3 different approaches here. So the green lines here are showing you that parallelism within the element, and you can see this is almost always winning for the hex. Whereas the blue line is showing you the parallelism where you're taking the interleaved data. And this, you see, is equivalent to the red lines, which is essentially using the standard matrix approach. To measure kind of how we're doing here as well, we're generally interested in throughput, i.e. how many degrees of freedom per second we can process. That's what you see on the y-axis, and then looking at that for a range of problem sizes from 10 to the 4 to 10 to the 8 degrees of freedom. And then, yeah, you can compare side by side and see some pretty obvious trends that, you know, hex outperforms the prism, outperforms square-based pyramid, outperforms a tetrahedra in general, which is kind of what you would expect, given that under the hood, the tetrahedron is still, in some sense, acting like a hexahedron because it lives on this kind of collapsed element space, plus the additional complexities that lie within there. But whereas you might expect that to be a factor of kind of 6 different, because you can kind of fit 6 tetrahedra in terms of their modes into a hex, it actually turns out it's not always that bad. It can be between a factor of kind of 2 to 5 generally in terms of reduction in throughput. So we're actually able to outperform what theoretically we should get in terms of the performance drop off. We also see that, you know, obviously going to higher polynomial orders on a hexahedron gives you a better overall throughput. And that's kind of a trend that's generally kind of reflected in the rest of the results as well. So this is the Helmholtz operator, but if you actually switch, and as well, we can do this to the CPU, sorry. The CPU results, this is a kind of lower grade kind of workstation kind of class, Xeon 6426Y. So you're kind of cache pressure limited here. But the interesting thing is, in this approach, where the red again is the standard matrix approach, this actually starts to win out now for a bunch of different the kind of tetrahedron particularly. This starts to win out for this Helmholtz operator. And if you're interested in, for example, the mass matrix operator, having this kind of standard matrix approach is really highly performant actually on the tetrahedra, to the point where it actually outperforms the hexahedra. So really, the thing I'm trying to point out from these slides is, if you're interested in the best possible performance, it's important to consider a range of different implementation strategies and how you lay your data out, as well as different element types, the operators, and so on. So for these kind of more arithmetically intense operators, I would say the sum factorization almost always is preferred. But in certain cases, these matrix approach, these kind of matrix-based approaches can outperform, and in some cases outperform considerably. In terms of the GPU different parallelization strategies, what we generally found is that this crossover point between whether you thread over the element and whether you thread over the quadrature points of the modes really depends on, first of all, your GPU hardware, but on essentially register pressure. So once you start getting above a certain polynomial order, what the figure on the right shows you is that you start basically running out of registers. This then causes you to spill over into local memory, and makes the approach a lot worse in terms of performance. And in 2D, it's a little bit more, there are particular crossover points. So you see for the quadrilaterals, order 3 and 4 are actually quite efficient under this kind of interleave type approach. But in 3D, probably almost always better to use that entry by entry approach, where you're kind of parallelizing over modes. So the summary from my part, and the kind of redesign efforts we've been going through, is that if we're interested in the best performance we could obtain with the hardware, there's actually really quite a significant number of critical parameters you have to consider. The polynomial order, which again, we might choose to vary in different directions within the element, shape type, implementation approach, whether that element has a constant or variable Jacobian, because you can make certain optimizations if you know that it's constant particularly, quadrature order, and often the case for these kind of LES simulations that we are using some form of de-aliasing because our integration order isn't sufficient to resolve these nonlinearities. And as well, basis type. So for example, I've shown you everything with a modified basis or IC0 basis. If you had a Lagrange basis and you chose to run in a collocated manner, then you can have specialized, even more optimal versions for some of these operators like the mass matrix, which becomes diagonal. So we'd like to be able to kind of capture and encode that. As well, we often want multiple data type implementations of these. Double precision is where we are at the moment anyway, and where I hope we can stay for the moment if the hardware keeps going that way. But certainly single precision is there, and if not for the solver, then the preconditioning one would typically like single precision, or even maybe think about half precision for the actual preconditioning of your overall system. And not to mention the hardware. Even between different CPU models, we see really significant performance differences, depending on cache size and so forth. So this is where I kind of stopped, but I thought I would motivate them why we are looking at this thing, NektarIR. Our current approach, everything I've shown you here, is relying essentially on C++ templating and us kind of pre-compiling essentially a whole bunch of different choices that we think our users would make the most use out of. Because we don't want to kind of restrict the ability of our users to have to recompile the code every time they want a different polynomial or defer simulation. So that's actually very effective. You can do all the optimizations you need to do. It's a little clunky in some cases, particularly kernel fusion, which is really important, can be very clunky if you're relying on kind of traditional C semantics. But if you're interested in all the different parameters I just showed you, you'll get an absolute ton of parameter explosions in the kind of most general cases. So we have fallbacks, but it's not ideal. And it also, particularly kind of kernel fusion and being able to kind of chop and change code around becomes quite difficult. So one could think about moving towards something like code generation, and we thought for a while about doing something like a source-to-source translation, which is, used very many other places in the finite element world. But we kind of thought about what we wanted to achieve with that. Well, really, we want to capture as much optimization at different levels as we can. So, for example, that collocation property, we'd like to exploit that, knowing what we know about that at our particular domain level. We want to be able to target different architectures, and we want to potentially optimize for those. We're quite keen to have this just-in-time compiled. So if you're running a big adaptive simulation where you might be changing a whole bunch of these parameters on the fly, it's very useful to be able to just fire off a request and get a function that you can then call to evaluate those operators without having to go away and sit and wait for a compiler somewhere to spit out the solution and write it to disk, load it back up, and so on. So we're quite keen for this to be just-in-time compiled. And as well, we didn't really want to build everything from the ground up. If you've ever tried to do this kind of stuff using just your own basic, writing your own kind of just-in-time compiler or instruction code emitter, it becomes very, very difficult, and you'll be targeting very specific architectures. So you really want to leverage the incredible technology we have out there from our compiler vendors and so forth in order to get the best performance. Otherwise, this would become a completely intractable task for what is a relatively small team of people. So to this end, we're really building this intermediate representation, which is what IR stands for, which represents these operators. And this is what Edward's project at King's has been working on for the last year and a half, 2 years or so. And really the aim is for us to capitalize on the existing infrastructure within this LLVM project. So this is where I kind of stop. I'll stop sharing my slides and put myself on mute, and I'll hand over to Edward for the rest of the talk.
Everyone can see this. Yeah, so in my part of the talk, I'm going to be discussing sort of the development of our domain-specific compiler so far. I'll start by sort of explaining what MLIR and LLVM are, how we use them, and why they make developing a domain-specific compiler easier. Next, I'll show off our abstraction and the MLIR dialect we have developed for these elemental operations, sort of what the IR looks like, as well as some of the design principles that have guided us through the development so far. Then I'll highlight the compiler pipeline. So how do we go from these kernels in our IR to CPU and GPU just-in-time compiled kernels, and the pipeline through MLIR and LLVM that we use to achieve this. Then I'll briefly look at some performance, including a runtime comparison between our NektarIR kernels and the Nektar++ redesign kernels, as well as the overhead that our abstraction introduces when we compile these kernels. And finally, I'll briefly mention the state of the code and perhaps indicate if where to go if someone's interested. So to start off, if we look at the LLVM compiler infrastructure, basically what LLVM is a collection of compiler toolchains or libraries that make developing domain-specific compilers significantly easier. The way it does this is by standardizing the conversion between a source code or source language and hardware target using an intermediate representation called LLVM-IR. So once a source code has been translated to LLVM-IR, which you can write either manually or construct programmatically, this intermediate representation can be compiled to the desired hardware target and vendor. And LLVM supports a multitude of backends, so hardware extensibility is really ensured through there. Some example projects where you will have found LLVM is such as stuff like the Clang C and C++ compiler, and the programming languages Rust, Julia, and Swift. LLVM-IR itself is an assembly-like language that uses static single assignment form, meaning that every time you have a variable, it can only be assigned a value once. And this makes it much easier for certain compiler optimizations that come in the form of compiler passes to be implemented, as stuff like use-def chains of a variable are much easier to determine. Now, while LLVM-IR is very powerful at what it does, since it's an assembly-like language, it might be too low an abstraction for several applications. It is perhaps not desirable to develop your code in assembly. And it might also be too low an abstraction for some kinds of optimizations that might benefit from being performed at a higher abstraction level. To this end, we have MLIR, which exists in the LLVM umbrella, and it stands for the multi-level intermediate representation. Now, how this works is by having several different abstraction layers of different operations that can be lowered and converted between. We'll see more what I mean by that in the next slide. But what it does is, for us, is it makes it much easier to interface with LLVM and build a compiler. You don't need to go directly to the assembly-like stage. You can start at a higher abstraction and then transcend slowly. MLIR itself has been used extensively in AI and machine learning applications, such as the backend for TensorFlow and the new programming language Mojo. It's less popular in scientific computing for now, but it has been used in the past in, for instance, the development of the OpenEarth compiler, where MLIR was used to accelerate stencil-based climate simulations. So MLIR itself uses dialects, which are groupings of functionality at a particular abstraction level to represent these operations. So you'll have sort of dialects for high-level constructs that you're familiar with from code or from programming in general, like the func dialect for functions, or SCF for structured control flow like loops, and memref for sort of shaped memory region representations. But there are also architecture-independent abstractions of specific hardware implementations, like the GPU dialect for vendor-independent GPU operations, and vector dialect for SIMD implementations for instance, AVX or SVE for ARM. These dialects have their own operations, types, and attributes, which are entirely reusable across different MLIR dialects. So once you interface with MLIR, everything that's provided upstream is made available to you. You don't have to reinvent the for loop, for instance. IR itself can be rewritten and lowered using MLIR passes. So to illustrate this, we have a pretty simple example. So you can consider the dialect, the dialect linalg is used to represent sort of basic linear algebra operations like a matmul, for instance. This will be converted first to the structured control flow, arif, and memref. So the mapmul goes from a basic operation to a set of loops that perform the reduction that you're after. These dialects are then further lowered to the LLVM dialect, which is a low-level MLIR dialect, which is direct representation of LLVM IR itself. And once the LLVM dialect is translated to LLVM IR, you can use LLVM to just-in-time compile your kernel to the desired hardware target. These IR rewrite patterns are not just for lowering and converting between dialects, but can also facilitate optimizations. One example of this is a very basic rewrite pattern that identifies a redundant operation. So in the example that I've got here, we have a function with a redundant transpose operation, basically the identity, which in MLIR would be canonicalized away using a canonicalization pass. But your traditional compiler might not be able to identify this redundancy and remove it itself. So our goals with using MLIR is to create an abstraction of common finite element operations at the elemental level and implement them using an MLIR dialect. What we want to do really is facilitate the just-in-time compilation of high-order, in particular finite element kernels, for use in CFD solvers. And we really want to leverage LLVM and the JIT compilation to support both CPU and GPU hardware. So the dialect design itself, so as I mentioned, we are at this abstraction level of basic elemental operations acting on blocks of alike elements in a mesh. So these blocks are sorted by the element shape, the polynomial order, the cubature order, the expansion type, and the cubature type, for instance. Some example operations that we have here is like the backward transform, basic inner products, and some collocation differentiation. And importantly, we want to continue this static single assignment form. So each elemental operation needs to produce a result that we can then use compiler passes to optimize and analyze further on down the line. Importantly, we don't use destination passing style or in-place operations. So each operation has a result, and we do not modify the destination buffer until we store to it. What that means, I'll show in a second. So for some IR examples, we can first consider a basic backward transform kernel. If I draw your attention to the first 4 lines of this IR snippet, we have the 2 block types, one for the coefficient space block, which we encode using the basis attribute here in the top right, here indicating that it is a modified C0 basis. And since we have free, it's a tuple of free modified keywords, this indicates that we're using a tensor product expansion. It's for hexahedral elements. The physical space block we indicate with the quadrature rule, which in this case is GLL, and we match the number of quadrature rules to the number of bases for each of the expansions. If we move down the IR a little bit, we get to this function operation, which basically indicates what the signature is going to look like once this is compiled, and so what the signature on the C++ side is going to look like once this is called after it has been just-in-time compiled. We move one step further. We have these operations that bufferize to tensor. This facilitates the conversion between a memory buffer and a immutable tensor-like type. So we don't work directly on the buffer at this abstraction level. Rather, we work on a representation SSA value representing the buffer. We facilitate something similar here using the block from memref operation, and essentially associates the input buffer containing the coefficient data to the coefficient block type. This block type is then passed into our backward transform operation near.nir.bwd, which represents the backward transform or the action of the tensor product bases on the coefficient block. The resulting type is a physical block type, indicating that we're now sort of in physical space. And then this final operation tells the result where to go in memory in this output buffer that we determined in the function signature. So a perhaps more complicated example of an operation might be the Helmholtz operation, for instance. In this case, the operation itself might be acting on blocks of elements, and our first lowering step will be to lower from a operation that acts on a block of elements to a loop over elements and a set of elemental operations. This allows us to effectively inline and fuse the kernels for free. So if we look at this next IR snippet, which might be somewhat difficult to read, so please lean in, everyone. Then we have at the top, we have a loop over elements and an extraction that extracts the single element for both the coefficient, the input modes, and the Jacobian. Next, we have this collection of elemental operations to perform the full weak Helmholtz operation. So like the backward transform, the differentiation, the application of the weights and the Jacobian determinants, as well as the appropriate inner products and tests against the test functions and the gradient of the test function. Finally, this operation can then be reinserted into the original block before being yielded as the result of the loop nest. So all in all, this IR snippet just represents a fused Helmholtz kernel where the fusion basically comes for free because of the loop over the elements and these individual elemental operations. We don't need to explicitly inline anything. If we then look at the pipeline, so how do we go from NektarIR, our abstraction level, to just-in-time compiled kernels? Well, it starts with a conversion to loops at either the affine dialect, which we'll talk briefly on in a second, the ARIF dialect to perform mathematical operations, and then memref and bufferization for the memory handling. The next step will be to convert this to LLVM for a simple kernel. If you're, for instance, targeting a SIMD architecture, you will then go to the vector dialect instead, and then to LLVM. If you're targeting the GPU, you'll go to the GPU dialect, and then depending on the vendor you're going for, there are several vendor-specific dialects that you can convert to and lower to, such as NVVM for NVIDIA in this example. There are other vendor-specific dialects available in upstream MLIR. The GPU part of the kernel will be compiled to a GPU binary using the desired GPU compiler, and then the host part of the kernel will be transformed to LLVM IR. Finally, these can be just-in-time. The host part can be just-in-time compiled for the desired target, and then this can be called from your application. So on the CPU side, this will return a function pointer that will execute the function that you've generated on your CPU. And if your target is a GPU, you create a host function which will invoke the GPU compiled binaries and start the process on the device that you're targeting. LLVM is quite extensible, so it also supports other targets. We just haven't gotten there yet. It's not on the slate for now. GPU and CPU will be enough. In terms of an interface, we don't really want you to have to write the IR like I briefly showed earlier. We rather want to facilitate programmatic construction of the IR using a C++ IR generator library. If you pass in the operator and mesh metadata to this or the operator, sorry, data to the IR generation library, this can then be passed on to our to a wrapper that we've developed around the LLVM execution engine, which facilitates just-in-time compilation to the desired target. The JIT library will create a function pointer to the compiled kernel that then you can call from your application. Down the line, we hope to have Python binding supported as well, but for now, the C++ interface is what we have. In terms of performance, it's natural to, at this point, even though I'm going quite fast, to ask sort of how long does it take to lower and compile a kernel for a specific target? Is there a difference in the overhead or in the cost of this abstraction for CPU and GPUs? And do we incur any costs or any advantages in terms of runtime? So for our performance comparison for the runtime, we compare both vectorized and GPU kernels from NektarIR and the Nektar++ redesign. On the host side, we do it's an AVX 512 intrinsics on 128 cores on AMD EPYC 954 CPUs. On the device, we're just using an NVIDIA H100. For the overhead, we're interested in the wall time from initializing the lowering pipeline from NektarIR to the LLVM dialect, and then finally the time to compile. So it's important to note at this point that the operators are using the matrix-free and sum factorized format that Dave showed earlier in their implementation. So what we start with some tetrahedral elements with the backward transform. On the y-axis, you have the throughput, so the degrees of freedom per second, and on the x-axis, you have the degrees of freedom for increasing polynomial orders from P1 to 9. The left figure shows the NektarIR performance, and the right one shows the Nektar++. So what we can immediately see is for low to sort of 4 or 5-ish polynomial order, maybe even 6, there are significant advantages in terms of throughput for the NektarIR cogent kernel. But as the problem size increases in this region down here, we see slightly worse performance and a bit of a drop-off compared to Nektar. The vectorization strategies themselves only differ in the fact that in NektarIR, we use a scalar load and then a broadcast for the basis data, whereas in Nektar++, they're stored in vector width number of copies of the basis data. So perhaps we're seeing that the broadcasts lose their, or the value of doing these broadcasts versus the alleviation on cache pressure decreases as the problem size gets large enough. It remains to be investigated further to determine exactly what's happened. If we move over to hexahedral elements, we see pretty much the same pattern repeating itself here. Better throughput early and for medium to high polynomial orders, but it doesn't stay better, basically. If we then move on to perhaps a more interesting operation such as Helmholtz, we start this, and this is on a hex. We see similar pattern repeating itself here. There's better performance for NektarIR compared to the Nektar kernels, but this sort of advantage of using NektarIR decreases slightly as the polynomial order increases. However, it's worth noting that this Helmholtz kernel is naively implemented using the IR I showed earlier, and if we change our compiler pipeline slightly to take advantage of MLIR's polyhedral loop transformation, polyhedral optimization dialect, affine, we can perform loop fusion, and the advantages in terms of performance that we get are quite nice. So if you call loop fusion, which is basically just adding one more pass to your compiler pipeline, we're able to increase our performance quite a bit and outperform the corresponding Nektar kernel across the board. which is quite nice. At the highest polynomial and order and problem size, it's only about a 1% difference, but we'll take any wins we can get, so that's not bad. If we then turn our attention to some device kernels, or actually, rather, if we now look at the comparison in the overhead costs for the time to lower and time to compile for these kernels. So on the left-hand side, we have the time to lower. So this is the wall time it takes from NektarIR expression level to the LLVM dialect. And we see for the fused kernel, it takes longer than for the non-fused one. For the loop fusion, sorry, the kernel with loop fusion takes longer, but still only 0.3 seconds. It's not long at all. And in the context of a long CFD solve, I would say that this is probably negligible. On the time to compile side, we see similar. It does not take long to compile at all. We do see increases somewhat with polynomial order, at least up to p is equal to 7, probably due to the increased complexity in the kernel and in the loop structure. If we now turn our attention to device and GPU code instead, we see not the performance gain that we would like, and I would like to emphasize here that we only just got the GPU lowering to work. So we're really highlighting here, rather than performance on the GPU, we're highlighting the fact that we're able to generate and execute these kernels from a single framework onto both CPUs and GPUs by only changing the pipeline, but that we compile slightly. So this is with the threading over elements approach. We can move on and then consider also tetrahedral elements. And we see the similar thing there where the performance is slightly, needs some improvement to meet and match Nektar. This continues for Helmholtz as well. But if we then turn our attention to what's the overhead cost on a device kernel, we can look at the next figure where we see the mean time to lower and mean time to compile for the NektarIR backward transform inner product mass matrix and Helmholtz. We see that the Helmholtz is the slowest to lower and to compile, but in both cases, it's still fast across the board for polynomial orders, where lowering in 0.2 seconds and compiling in 0.303. I'll mention that the reason why the time to lower is so much higher than the time to compile is that in MLIR, the GPU, the actual GPU binary is compiled the IR is compiled to a GPU binary as part of the lowering pipeline. So that's why you'll see the lowering time be higher than the compile time. There's not a lot of host kernel besides calling the device kernel on that side. So for a summary of what we've shown here, we facilitate the code generation of just-in-time compiled kernels for both CPU and GPU targets from a single representation using MLIR and LLVM. We see good performance on CPU without many optimizations, but we can optimize to get even better. The GPU kernels need some optimization, but I want to emphasize again that the MLIR framework gives us complete control of the kernel from math to metal, if you will, and lots of optimizations remain to be tested. Theoretically, you could do whatever you want with the IR to optimize it at any abstraction level as you lower towards LLVM before compilation. So that's sort of the focus of our future work. We want to optimize to get better performance. We want to test on more hardware. We want to get the operators working on all of the shapes. And a particular focus interest would be to expand to more basis types, such as nodal expansions, and investigate sort of how to neatly implement the collocation property for Lagrange polynomial type bases on both tensor expansion elements such as the quad and hex, and the collapsed elements with the triangle, tetrahedron, prism, and pyramid. In terms of the code itself, the idea is that it will be open sourced and independent of Nektar++. It's nearly ready for release, but if you want to access it, you can just contact us and we will let you have a look. Thank you very much for listening.
Hi, I'm Andrew, and I have a question. So you had mentioned that we're doing this loop folding kind of optimization. Is there a similar one where you can do like kernel, like automatic kernel fusion for you, like analyzing like the size the kernel is, or other parameters of the generated kernel to decide when is the best point to fuse different kernels? Or is that's still like a user responsibility to decide how to split the kernels?
So I think Edward probably is the better person to answer, but I think at the moment the focus of our kind of local elemental operations is our observation generally is you pretty much always want to kernel fuse as you loop over elements, and this is that principle of just doing as many flops as you possibly can with the data that you have from memory. There is a bit of a limit, having said that, in terms of one potential source of our kind of GPU issues right now might be that we have just too much register pressure. So yeah, this is definitely something for us to kind of look at a little bit further in terms of our optimization strategies. Like, I don't know whether, Edward, you want to say anything else?
Well, I can, I guess, add that in the representation that we have currently, in, for instance, the lowering of a block Helmholtz operation, the kernel fusion is essentially always going to be there because the operations are going to be automatic inlined. If you want to look at sort of alternative approaches to maybe splitting that up into, say, one kernel for the Laplacian part and one kernel for the mass part, and then adding them together, that would be an alternative investigation and would be pretty trivial to implement in the MLIR format because it's so flexible at just splitting the IR up in however way you want. We just haven't gotten there yet.
Okay, thanks, Andrew. Anybody else?
Hi, this is George. Can I ask a question?
Yes, please, Georgis.
Thank you very much for the talk. This is really good work. One question that I have, actually, it's two questions. One question is, how do you interoperate with C++ code? So, how does one use the NektarIR generated code from the C++ main driver of the application? And the second question is more of what's your experience with the MLIR ecosystem, the volatility of its development, and basing on that?
Yeah, those are really great questions. So in terms of the first, we basically have this IR generator kind of utility class, I guess I would call it, where you have the option either of, I guess, writing either your own IR or for certain, very, very common operations like a backward transform, we provide you like a C++ signature, say, okay, I want, this number of modes, this basis type, etc. That will go and write the IR for you and then run it through the LLVM execution engine. And then from that, you'll get returned a function pointer. And so you can then from the C++ side just call that function pointer like it's a regular function. So that's the bit we're kind of still needs a little bit of tidying, but the concept is basically how we would envision people using it. The second question you had, it's challenging. MLIR is kind of one of these very rapidly evolving projects, and it's driven by lots of different needs. So the dialects change quite frequently. It's not always kind of easy to keep up with the changes that are made between different LLVM versions, particularly. So our strategy really has been to pin down a particular LLVM version, and then once we realize we might need some functionality from a later version, go through a little bit of pain to update from one version to another. And I think that's a fairly kind of common strategy. I will say that the community there as well has been kind of very responsive to queries and such as well. So they we've spotted a few bugs and things that we reported upstream that then get fixed and so forth. So it is challenging. It's also, you know, if you've worked with LLVM before, just on a practical level, it's a huge project. It's complicated to use, so there is a certain barrier to entry as well, just in terms of that. But I would say overall, now we've kind of fought through the pain, so to speak, of kind of understanding the framework as non-compiler people as well, I would suggest. It's been quite productive.
Do you need to do any data transforms when you try to use the IR generator code from C++? I mean, your original data, do they need to change the layout of a memref, or do you assume that the application has already a memref abstraction?
So we have in the functions that we write for example, the backward transform operator, if you look in that block type as well, you'll see there's like a layout option that kind of determines the layout of the data, because there are a couple of different approaches that, you know, you could have data laid out in a couple of different ways, like I was saying in my half of the talk. So, I mean, ideally, you don't want to transpose between those, but in theory, you can specify a different layout, and then we would transpose on the fly, for example, and reorder things. But the idea is to kind of map it as closely as we could to whatever data you're going to give us.
Makes sense. Yeah. Yeah. Thank you.
Okay.
Thanks, Georgis. Okay, other questions?
It sounds like you have a lot of different optimizations you can try. So your search space might be pretty large. What approach are you going to take to explore the search space?
It's a good question. I think actually a lot of the parameters come down to a good chunk of the parameters come down to things that the user already gives us. So, for example, you know, they would typically maybe give us a polynomial order, or certainly the mesh element types and such. The geometry would be fixed, but there are so that kind of limits the search space a little bit. But there are other ones. There are certainly, you know, other you know, the implementation strategy that you would use, the layout of your data and such, that, you know, require a little bit of thought, I think, and maybe not so obvious for users to select as well. I mean, we see that already in the code just as it is without all the IR stuff. So, I mean, I guess one strategy we used quite successfully in the past is at least trying, given that these are fairly quick to compile and execute as well, to, you know, in the remaining parameters that we have, to do a little bit of auto tuning at the start of the simulation, or whenever parameter changes, assuming it's not, you know, a cost that is so large that it would really affect things. But you're right, there's a lot of kind of things that one might wish to tune.
Okay, thank you. Other questions? Maybe I can ask one. So, do I understand correctly that you guys now are focused on the elemental dense matrix operations? And have you looked at also including the global scattering and gathering from the non-duplicated degrees of freedom?
Yeah, we have. I don't have figures to show you because it's still a bit of a work in progress. But yeah, on the redesign aspect, we've got versions that have like multi-device assembly now and such. We're in a bit of a phase of trying to optimize those and see where we can make some gains. So we are doing it. It's that's the last step in terms of getting our solvers fully working. So we have versions that work, and we have now solver prototypes that are starting to work as well. But we need to do a little bit more optimization to get them working efficiently, I would suggest.
That's on the Nektar ++ side, not in the NektarIR bit.
Yeah.
We're not there yet, just on the elemental operations there.
Yeah, I think the ambition would be that we'd be able to do that. I think that's one of our tasks.
Yeah, one of the challenges there, the interesting thing is that they're more of a sparse matrix vector operations, and I'd be interested to see how the dense and the sparse portions of MLIR interact. For GPUs, you might want to actually fuse at that level, include the transfer and the scattering and the gathering in the assembly, for example. But the global,
exactly. Yeah, because I think as well, and that's the kind of thing actually that's proven a little tricky to do from kind of a pure C++ side of things. Just designing a framework and trying to make it flexible enough to be able to do all of that stuff is very difficult. So Yeah, this is where I think an approach like MLIR could be quite useful for us because we have a lot more flexibility in what we're able to do in terms of fusion and, you know, inlining different bits of the algorithm, trying a few different things.